Let's take a look at the mean value theorem. The mean value theorem is something you'll see referred to quite often in your study of calculus. So let's see what it says here. Let's suppose that you have a curve here, a function f of x. And we have some specific requirements for this curve. Let's suppose that it's continuous on a closed interval AB. Okay, so I've drawn you one here. It's continuous on this closed interval AB, and further, it's differentiable on that same interval, except maybe not at the endpoints. In other words, it's differentiable on the open interval. Okay, so maybe it's not differentiable at the endpoints. If that happens, if you have this situation, the function is continuous on the closed interval, differentiable on the open interval, then here's what you're guaranteed. There exists a c on this open interval. Somewhere in here there's a c such that f prime of c is equal to f of b minus f of a all over b minus a. Okay, so what does that mean? What does all that mean? Well, I'm going to illustrate with a picture here, and then to kind of help you see it with an application. But if you think about this, here's a and here's b, and here's f of a minus f of b minus f of a over b minus a. Well, think about this. If I draw a line here, okay, there, that line, and I've got this point up here, b f of b, and down here I've got a f of a. See? So there's this point and there's this point. The slope of this line right here, the slope is f of b minus f of a over b minus a. Now, let's think about this f prime of c. Remember, this is the average rate of change. This slope, the slope of this line, that represents the average rate of change from x equals a to x equals b. Well, what the mean value theorem is telling us is somewhere up here, there's a tangent that is parallel to this line. Now remember, so let me just go down here. There is a c such that the slope of the tangent is the same as the slope of this line. In other words, these two lines are parallel. There's a parallel tangent up there somewhere. So it tells us that there is a parallel tangent. So if you draw this line, you can take this and go up and find a tangent that's parallel to the secant. That's what the mean value theorem tells us. In other words, there is some place where the instantaneous rate of change is equal to the average rate of change. There's that tangent up there that's parallel to the secant. And you can kind of see how that has to be true if these conditions are met. Now, one of the ways to help you to understand from a practical sense, let's suppose that you're driving along and you drive for a couple of hours and you notice and you compute your average speed. Let's suppose your average speed, which would be like the slope of this line right here, the average rate of change. Let's suppose your average speed was 70 miles an hour. Well, you know that there was some point along while you were driving that your actual exact speed was 70 miles an hour. In other words, if your average speed is 70 miles an hour, at some point you were driving exactly 70 miles an hour. It can't be the case that your average was 70 and you were always driving below 70 miles an hour. Or your average speed was 70 miles an hour and you were always above 70 miles an hour. At some point, you were driving exactly 70 miles an hour if indeed your average speed was 70 miles an hour over the course of that drive. So that's what the mean value theorem tells us. The conditions for this to be guaranteed to be true was that the function is continuous on the closed interval and differentiable on the open interval. Now let's look at an example here. Let's suppose that we've got a function f of x equals, let's say 9 minus x squared on some interval. Let's suppose we've got -2 to -1. And what we want to do is we want to first of all determine, are the conditions for the mean value theorem met? And if they are, let's find a C where this is true. Okay, well, first of all, this is a polynomial. And polynomials are continuous and differentiable every place. So there's no worry. If we're dealing with polynomials, we don't even have to worry. They're continuous and differentiable every place. So what we need to do is we need to find the C. So first of all, I'm going to compute f of b minus f of a over b minus a. That's what I want to compute first of all. Now here's my a and here's my b. So let's see here. F of b, there's f of -1, minus f of a, f of -2, over -1 minus a -2. See, f of b minus f of a over b minus a. So let's see what we've got here. This is going to be f of -1 minus f of -2 all over, let's see here, this is -1 plus 2, that's just 1. Okay, now f of -1, well, this is just 9 minus 1, so that's 8. So here we go. We've got 8 minus, now let's see here, f of -2, that's 9 minus 4, so that's 5. So this is just 8 minus 5 over 1. Okay, good. So that's just going to be 3. That's just 3. Okay, now let's find the derivative. So the derivative, f prime of x, is equal to -2x. So I want to find my c. So I'm going to do this. I'm going to say -2c, I'll just replace x with c, equals 3. And what I get then is I get that c is equal to -3/2, and that's my c right there. That's my c. Now, that's all we were asked to do. We were asked to verify that the mean value theorem exists, or the conditions were met, and then if they were met, we were asked to find a C. Now, let's look at another one here. Let's suppose that we've got f of x equals, let's say, the absolute value of x on some interval. Let's suppose the interval is -1 to 2, something like that. Now, this is an absolute value function. And the absolute value function, if you look at it, remember what this looks like. Looks like this. Okay? It's got a sharp point right here at 0. The derivative would not exist at that sharp point. So, the mean value theorem does not apply. Yeah, the mean value theorem does not apply. Okay, so let's look at another one. Let's suppose that we have f of x is equal to x to the 1/3 on -1 to 1. Let's look at that one. Now, the reason this mean value theorem didn't apply here was because 0, a place where this function does not have a derivative, is in this interval. Now let's look at this one. maybe I can see that I don't really know if the derivative exists or not. Maybe I'm not familiar with this function. So how do you proceed? So here's what we can do. I can go ahead and find the derivative. This is going to be 1/3 x to the negative 2/3. And that is 1/3 x to the 2/3. Okay, so I differentiate it. Now, notice, once I differentiated it, I can clearly see that the derivative does not exist whenever x equals 0. Well, 0 is within this closed interval here, right? It's between -1 and 1. So, since the function, since f of x equals x to the 1/3, since the derivative does not exist at 0, and 0 is in that interval, the mean value theorem does not apply.